Let's look at and kind of go through this not so simple example of a decision tree. And sketching out this decision tree, we had this clinic deciding between two drugs to treat whatever illness we want to make up. So I've got my decision here. We had two drugs. So we had drug X, and go down here. We've got drug Y, right? And the clinic has to decide, should we go with drug X, should we go with drug Y, and based on estimates, which one's going to be the more efficacious. Let's start with drug X. That one's a little bit more the tricky one here in the given example, in the given prompt. So drug X, we've got this chance, right? And just like any drug whatsoever, right? It might work, uh, or there's another chance that it you know doesn't work. So we'll just put not work. So in that prompt, well, there's an 80% chance that it would work, 0.8, and that leaves us with a 0.2 20% chance that it won't work. Well, if it doesn't work, it doesn't work, and there are no um, additional additional lives saved, and that's our outcome. That's our output here. That's our quantifiable measure. So we're looking for the drug that saves the most lives. So if it doesn't work, well, it's not going to save anything. If it does work, well, we've got another kind of probability chance point here, because it might work, but there might not be an outbreak of that disease. I think that a little bit longer. So, you know, maybe there is an outbreak. Yes. And maybe there's no outbreak. Right? Again, apologize for my handwriting on this thing here. So there's an outbreak. Maybe there's no outbreak, and there's a probability for each of these as well, 0.4. So 40% chance that there's no outbreak leaves us with 0.6. 60% chance that there is an outbreak. So the drug in a drug X might work, but if there's no outbreak, well then there's no outbreak. There's no one to save. Whoops. Let me erase that real quick. That looks terrible. Right. So if there's no outbreak, again, that's no better. That's a 0. I'm gonna leave it there. There are no lives saved. If there's no outbreak, the drug can work perfectly, but if no one needs it, then no lives are saved. Well, if there is an outbreak, there are a few possibilities here. Another kind of probability spin-off here. Well, there's a chance we could save 200 lives, right? And in that prompt, there's a 0.4. We could save, or that clinic could save 100 lives. Again, 0.4. And then there's another chance we could save, looks like 60 lives. We end up with a 0.2. Right there, 20%. Again, we're making sure that all of our probabilities add up to 100%. So 0.8 plus 0.2, that adds up. 0.6, 0.4, that adds up. 4, 4, and 2, those add up to 100. So double checking ourselves as we go left to right. If we do this quick math, so estimated values, right? Remember, that's what we're going for. Estimated values. So 200 multiplied by 0.4 is 80. 100 times 0.4 is 40. 60 times 0.2 is 12. We're going to add all of these together, and if we add all of those together, estimated lives saved 132. So we've gone all the way to the right. Now we're going to go back to the left. So I've got 132. Well, now I have to multiply that by 0.6, because remember there's a 40% chance that there's no outbreak and we don't need any of this. So 0.6 multiplied by 132, come up with 79.2. 0.4 multiplied by 0, well, that's 0. So how many lives am I saving here so far? Estimated lives being saved so far is 79.2, but we still have one more step to go for drug X. And that one more step is to add these two numbers together. So 79.2 plus 0 is, well, 79.2. But there's also a chance that the drug X won't work. So 79.2 multiplied by 0.8, that 80% chance that it will work. And that's going to be our final number there. So if we multiply 79.2 by 0.8, we get 63.4 estimated lives saved if that clinic goes with drug X. Now if they go with drug Y, again, there's another little probability chance circle there. Drug Y, just like drug X, can work or not work, but in this prompt, I kind of split it out into three probabilities, or three possibilities. So first possibility is that it works, but it works really well. The drug works really well. Second possibility right here is that it works. Right, drug Y works, but just moderately well. That's an M. Just moderately well. And then, just like drug X, there's also a possibility that it doesn't work. If it works moderately well, I've got 0.3, 30% chance. Same thing with working moderately well. So drug Y works. There's a 60% chance it works, but it's split between does it work really well or does it work just kind of well. All these need to add up to 100%. I'm at 60% right now, so my leftovers 0.4, and that's kind of where we are right there. If it doesn't work at all, just like with drug X, 0 lives saved because, well, it doesn't work. We're going to go up to if it works well. I'm going to extend this out a little bit because we've got another kind of chance probability offshoots here. So just like with drug X, we had 3 possibilities. One is that it saves this through this clinic 160 lives, and there's an 80% chance of that. Chance that it saves 80 lives, there's a 10% chance of that, and another chance that it could save 30 lives, and there's a 10% chance of that. Let's do this math. 128, so 160 multiplied by 0.8. These two are pretty simple. 3 and 8, just like above. We're going to add together vertically and come up with 139. So right now, all the way to the right, 139 versus 132. It looks like 139 lives is better, greater than 132. So we're heading in the right direction here. We're going to start going to the left, but we still haven't figured out how many lives could be saved if the drug works moderately well. Well, in the prompt, it says if it works moderately well, saves half as many lives as if it works very well. So half of that is 69.5. Well, what do we do here? Now we're going to go from the right all the way to the left. So if I am going right to left, I've got 139 here. I'm going to the left. Well, I hit this 0.3 probability. So 139 multiplied by 0.3, 41.7. Same thing here, 69.5 multiplied by 0.3, end up with 20.9. 0 times 0.4 is just 0. So we're happy there. I'll just put a 0 right there. I'm not doing too well with my zeros today. Put a 0 right there. We're going to add these up vertically to get our final answer over here. If we add those up, oh, well, that was just terrible. If we add all of those up, we get 62.6. So there's my final right there. There's my final right there for drug X. Drug Y. Drug Y, just a little bit lower than drug X. So, based on this decision tree here, we should be going with drug X because it saves just a little bit more, or estimated to save some more lives. So, this is just another example of a decision tree. A little bit more complicated. There were a few more steps there. So as you're working through these prompts, through these basically word problems, just pay attention to where your branches are as you build your tree left to right, and then going right to left, making sure to keep your math um, kind of clear, concise, and in the correct columns as you go from right to left. You're multiplying by those probabilities to get your final numbers and which one is the best outcome.